Alright, let's get started with the first problem of the day, which is going to be LeetCode number 55, jump game. You're given an integer array nums. You're initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false otherwise. Okay. I think I've done this problem before, but it's been a very, very long time. It was either DP or greedy. The idea is that we can say whether or not we can jump to the next to the next block is contingent on whether or not we can jump to any previous block that can reach us. So I think the idea was that we would do a backwards DP setup. It might have been, yeah, I think it might have been that. So we start by creating a boolean array of the same size as nums. The first item, the last item is set to true. And this boolean array represents whether or not we can reach the last tile from that tile, right? So we know that given our circumstances, when we start at the end, we know that the last tile will always be able to reach itself because it's, well, the last tile. It doesn't need to move anywhere to jump. And then we check. So for each item after the for each item starting at the second to last to the beginning, check to see if there are any elements which we can jump to which have a value of true. If yes, we can set our own value to true and move on. Otherwise, we cannot reach the end from that tile. And then at the end, we would just return the boolean value at 0, index 0. This would take O of n squared time and O of n space, because the idea is that suppose that it was not possible. It was not possible to reach any element. So, for example, we have an array that just has a bunch of zeros. And if we could not reach the next element, or rather, if we could not reach the end, we would have to still exhaust the entire value of the loop, which can be as much as n minus k, where k is equal to nums at I. Right. So the idea is that no matter what, even if, as long as this has a value, we have to exhaust it. And if the value is limited at the max to be n minus the value here. The main idea being that we can't go beyond that, right? We can't go beyond the number of items that we have left. And so in the case that we actually do that, and we do something like, I don't know, like 0, 1, 2, something like that, then we still have to exhaust it, and that sort of stretches out to be O of n squared. So that's not really, it's not really a great method. Okay, so I think this method works. However, the constraints kind of scare me, because the n is at the most 10 to the 4, which kind of signals an O of n or O of n log n solution. And that kind of makes me think about whether or not there is some additional calculations that we can avoid here. Because having that amount of work would kind of be nuts for a 10 to the 4 solution. If dp is overkill, then that means that there is potentially there may be a greedy solution. Let's see. Is there a way that we could check all elements after our current in O of 1 time? Because if there is, then that could be the secret to, or that could be the key to getting a faster runtime solution. Well, we can say that if the value, if n minus the nums at I is less than or equal to 0, then we can reach the last element without going through intermediate elements, right? So for example, for here, this 1, we can just jump straight to 4, and it doesn't really matter. We don't need to calculate further than that, right? So if n minus, well, if n minus, let's see, I think it's I plus 1 is less than or equal to nums at I is what we actually want. So our current index, or the current distance between the end of the index and us, so n would be 5 here, and our value here would be at 0, 1, 2, 3. So 5 minus 3 is 2. Maybe we want to do minus 1. Actually, yeah, n minus 1, because we want to reach the end, right? So 2, 3, 4, 5 minus 0, 1, 2, 3. So 5 minus 1 is 4. 4 minus 3 is 1, which is less than or equal to nums at I. Then we can just reach our last element, no problem. Same thing with this one, right? 1, 2, 3. This is 4 minus 1, which is, 3. And that's exactly equal to 3. And so we can jump to the last element. So that's one way that we could handle it. The question really then becomes like, is there a way that we can optimize the case where it's not? Like for example, this case, right? 0, 1, 2, 3. Oh, we won't ever reach this last element, but is there a way that we can speed up that process? If we had a let's see. Maybe if we did, right now I'm thinking of maybe something to do with bits slash bit manipulation. So we had one that was like, for example, let's do 0 for false, 1 for true. And let's say that we're at this cell right here. So we know that the 0 right here will be false. But what about this one? Well, what we could do is create an alternate space where we do this instead. Where we say that, okay, we set the 1 bit to reach the second to last element. And does that reach? No. Because the idea is that if we AND them together, that equals 0. Whereas if we had a case like 2, 3, 1, 1, 4, that translates to, let's just say that is the case, and we do something like this, and then we do 0, 0, 0, 1, 1, or 0, like that, and we AND it together, we get something that isn't 0. But still, even in the case of this, right, if we were here instead, then we would have to apply them. We would say, like, we would have to create like something. We'd have to create this binary string. And I'm not sure if there's a way to do that efficiently. There might be a way to do this efficiently where we create this string and then this binary string and then we AND it together. Let me think about this. Is there an efficient way that we could mask this such that it would work the way that we expect it to? We could bit mask away the last element, no problem. We can just AND the last one with the 0. But the real problem really is the middle elements. I think I'm just going to go ahead and code the DP solution first, and then think about this greedy solution and building on it once I have time, after I've built up the DP solution. So let's go ahead and start with that. We'll say can reach array is equal to bool array of size nums.size, and we just initialize them all to false. And then we can say for, well, can reach end or array at nums.size -1 is set to true. And then for index in nums size -2 all the way down to 0, we can say for inner index from index to nums.size or nums.size -1 if can reach array of inner index is equal to true, then we can say can reach array of index is equal to true, and then we break out of that. We can also say if our current nums.size -1 minus our current index is less than or equal to the numbers at our index right now, then can reach array at index is just going to be set to true. And if the current value is still false after that, then we can do this, where we go through the rest of the loop. And then at the end, we can just return can reach array at 0. So that's pretty much the DP solution there. So we create a boolean array. We set the last one to true, and then we start from the second to last all the way down to 0. And we say that if either the like the difference to the end is less than our current index, or if we can reach another index which can reach the end, then we can set our current value to true, and then we can break out of this loop. And at the end, after we go through each element, we'll just return the first element, which indicates whether or not the first element can reach the end. So let's go ahead and run a compile on this. Let's see. In. That should not be from. Let's see. That should be fine. This might need to be boolean array. This inner index should work now. This break doesn't quite work here. We can say var inner index is equal to index, while inner index is less than nums.size and and not can reach array at index is equal to true. And then we can sort of move this up. And then we can increase inner index by 1 each time. And that should do effectively the same thing, but now we should be able to essentially break out of the loop. by just doing by just setting the can reach array at index true, since this will be evaluated each time. Let's go ahead and run this again, and let's see if there's anything up with it. Let's go ahead and run both of the examples. Looks like it works for the first one. Let's make sure it works for the second one too. Interestingly, it doesn't seem to work for that one. Let's see. Let's see, that's 1, 2, or 0, 1. That's 5 minus 0, or 4 minus 0. 4 minus 0. 4 minus 0 is not less than or equal to 3. Let's see, 0, 1, 2. 4 minus 2 is 2. Interesting. Let's take a closer look at why this is happening. While inner index is less than... Oh, we want to go to size and let's see. Inner index minus index is greater than or equal to 0. Or greater than or equal to nums at index. Less than. So the idea is that we want the difference to be less than or equal to. Actually, we can just be less than, right? The idea is that 1 here, this 1 here, we can start at the next element. And we say that, okay, so this next element, the difference is 1. 1 is not less than 1, so we need this less than or equals to now. Because 0, 1, 2, and 3, so the difference is 1. We still want to check this item at num's index to make sure that's we exhaust all the elements, but not all the elements until the end. So this should work now. I think the problem before was just that we were checking all the elements until the end of the array without stopping for the actual, like, instead of actually, like, stopping at the, like, the difference here. So that works. Let's go ahead and throw in a submit to see if the LeetCode problem on this one is lenient. Okay, so the runtime seems to suggest that this is actually perfectly fine. Like an O of n squared solution is fine. Which is weird. So maybe there isn't a greedy solution for this, because the runtime seems to suggest that it's about average. I'll probably think about this more off camera, but honestly, it might just be a dynamic programming approach. Maybe. But in any case, a dynamic programming approach I think makes the most sense. The subproblem is essentially that for each item, for each cell, we check to see if there are any cells within jump distance that can reach the end. So that is the subproblem that we do in order to produce our dynamic programming solution. This uses a for loop, technically nested for loops. I used a while loop here so that I could break out of it easier. But if you want to use a for loop, that's also fine. In any case, I hope you learned something, and I'll see you for the next problem.